Okay, so like we did with arithmetic sequences, the next step is to look at geometric series. And just like with the arithmetic, a series is when you add the terms of a geometric sequence together. So, for example, we've got an example like this where we've got 3 plus 6 plus 12 plus 24. And we can see that this is a geometric sequence because each time the term is doubling. So we know the common ratio is 2 and the first term is 3. And just like the arithmetic series, there is a formula for this. And we've got to work it out. So we're going to do this algebraically to begin with. And we know the first term is A. And the second term is A times R, so it's AR. And the third term is A times R, so that's going to be AR squared and AR cubed, all the way up to the last term, which is going to be AR to the n minus 1. Now, if I wrote this backwards and tried to add them together, it's not going to help. So I have to use a different technique for this one. And what I actually do is, I say I'm going to multiply everything by R. So I have to multiply every term by R. So I end up with R times S equals A times R plus, let's multiply the second term by R, it's going to be AR squared. Multiply the third term, is going to be AR cubed, AR to the power 4, all the way up to AR to the power N. Because if I do R to the N minus 1 times R to the 1, what do I do with those powers? I add the powers, so I get R to the power of N. Okay? And then we do something that's a bit clever in a way, because I notice that there's a lot of common terms here, because I've got AR in both of them, AR squared, AR cubed. This would be the same as this, and all the way up, you would dot and it'd be the same. And the second to last term here would be the same as this term here. So there's a lot of terms in common. So what we actually decide to do is, we decide to subtract. Okay, and if I call this equation 1 and this equation 2, I do equation 2 take away equation 1. So on the left hand side, I've got RS take away S is equal to, and like I say, if I do this take away this, they go, they go, they go, all of these go, and all I'm left with is AR to the power N minus A, and that's it, because all I had left was this take away this. And this is really nice. So I can think, I'll factorise this. So I can take a common factor of S out of the first one, so I've got R minus 1. I can take a common factor of A out, so I've got R to the N minus 1. Now I can actually find an equation for S, and if you remember, S was the sum of my series, and so I say S is A, R to the power N minus 1 over R minus 1. Okay? Now, you sometimes see it in a different form, because sometimes what I could have said was, subtract 1, do 1, take away 2. I could have said, let's take equation 1 and then subtract equation 2 from it. And in that case, I would have just had it the opposite way round, because I'd have just had S take away RS is equal to A take away this term here, which is AR to the power N. I do exactly the same steps now. I say S is 1 minus R equals A is 1 minus R to the N. And so my S is A times 1 minus R to the N over 1 minus R. And actually both of these are true, because if we think about it, if I multiplied the top and the bottom by minus 1, which with equivalent fractions would keep everything the same, I'd have A, and I'm going to times, that's the first term in the bracket by minus 1, times the second term in the bracket by minus 1, minus 1 plus R, and actually then that becomes the same, because it's just S equals A times R to the N take away 1 over R take away 1. So it doesn't matter which form you use, whether you do it this way or this way. And sometimes it can just be a bit of a habit as to which one you use. I tend to use the second one because that's just how I write it. And that's the form that I remember in my head instantly. Okay, now you do have to be able to reproduce these proofs in the exam, but don't worry about it yet. The exam's a long way off. We can recap them nearer the time. So let's have a look at some problems then. So let's have a look at the one we started with. So as I said, we know that the first term is 3. We know that the common ratio is 2. I'm going to write my equation down, which is 1 minus r to the power n over 1 minus r. So actually, we need to know what n is. And in this form, we don't know what n is. We don't know how many terms are in this series. So we have to work it out. And just like we did with the arithmetic series, that's our last term. So we know un is 1,536. So we know ar to the power n minus 1 is 1,536. We substitute in what we know. So we've got 3 times 2 to the power n minus 1 is 1,536. Divide by 3 is, I can't remember what it was, 1,536 divided by 3 is going to be 512. And then we use our logarithms again. So because it's 2, it's nice to do base 2. So I say that's log to the base 2 of 512. So log to the base 2 of 512 is 9. So that means n minus 1 equals 9. So n equals 10. And now I've worked out what my n is, I can just substitute everything into my formula. And what we tend to do is when we write s, because the sum of a series depends on how many terms there are, we tend to put how many terms as a subscript. So we say the sum of this series for the first 10 terms, and we don't denote that as s subscript 10, is 3 times 1 minus 2 to the power of 10 over 1 minus 2. And here you just use your fraction button, you type it all in. So 3 brackets, 1 minus 2 to the power of 10, close the brackets, and in the denominator 1 minus 2. And you end up with our sum of our first 10 terms in the series is 3,069. Okay, so let's have a look at another one. So find the sum of the geometric series here. So we've got exactly the same problem, it's just a different series. So again, our A is 1024. Now, what's the R going to be? 1024 times what makes minus 256? Well, we know it's got to be negative because we've took a positive number, we've multiplied it by something and got a negative number. And 256, how many 256 goes into that? And so it's going to be times a quarter. So my common ratio is a quarter. Okay. Again, we don't know what n is, and unfortunately, we need to know what n is to be able to use our formula, which is that. So we know the nth term is minus 1/16. So let's work out what that is first. So we've got AR to the n minus 1, because that's what the nth term is in a geometric series, is minus 1/16. Now, we've got, let's think, we've got A is 1024 times minus 1/4 to the n minus 1 equals minus 1/16. Divide by 1024, so we've got minus a quarter to the n minus 1 equals minus 1 over 16 times 1024 is going to be, big number, 16,384. Now, you're going to have a bit of a problem now, because if I decided to take the logarithm of both sides, which I could do, I could say try and do natural logarithm of minus a quarter to the power n minus 1. So I'd take the n minus 1 out and put it at the front like that, like we did before. equals the natural logarithm of minus 1 over 16,384. If you try and do that with your calculator will go math error. And that's because you can't take the logarithm of a negative number. Because if you think about the graph of logarithms, goes like that, it is never in the negative x. So there's no such thing as a logarithm of a negative number. So you can't do it. So we have to think what we could do instead. And what effectively we need to do is we need to get rid of this negative. And the way we do that is, the easiest way to think about this is, if I multiply through by minus a quarter, then it will work. Another way of thinking about it is actually, if you just did it with a quarter and with 1 over 16,384, you should get the right answer. But if I multiply through by minus a quarter, I'd have a quarter to the power of n is equal to 1 over 16,384 times a quarter. Okay, so now I could do the natural logarithm. So I'd say n, the natural logarithm of a quarter, is equal to the natural logarithm of 1 over, and that times 4 is 65,536. So n is going to be the natural logarithm of that one over the natural logarithm of a quarter. Okay, so natural logarithm of 1 divided by my answer divided by the natural logarithm of a quarter, and you get n equals 8. Now whenever you've had to do something like this, I would always check, okay, because what I did here wasn't strictly mathematically correct, because it depends on whether n is odd or even, whether that is true or not. Okay, so you should always check. Chances are it is going to be correct, but I would always check. So I'd say, well, what is U8? What is the 8th term? 1024 times minus a quarter to the power of n minus 1, which is 7. And when you put that in your calculator, you do get minus 1/16. So it was correct and it was okay. So we know what n is now. We know all the information that we need. So we can just put our sum of our first 8 terms is going to be 1024 times 1 minus a quarter to the power of 8, because it's to the power of n, all over 1 minus and minus a quarter, because that's what your common ratio is. So you can see you've sort of like got double negatives going on here. But again, just pop it in your calculator, use your fraction button. 1024, open the brackets, 1 minus, I've got to be honest, with easy fractions like that, I turn them into decimals, so I do minus 0.25 to the power of 8, just because it's easier to type, over 1 take away minus 0.25 in the denominator, and we end up with our sum of 819.1875. And at first you might think, hold on, but that's smaller than the first term. But remember, we've got a positive and then we're adding a negative term, then we're adding a positive term, then we're adding a negative term. So it's forever going up, then down, up, then down, up, then down. Okay, so in a way it should be smaller than the first term because each subsequent term was getting smaller. Okay, so let's have a look at this. Then we're going to get the ones where we're talking about the sum exceeding a value. So find the least number of terms such that the sum of this geometric series exceeds 1,000,000. So again, we know A is 5. We can see R is 2 because each term is doubling. Okay, we want to know when Sn, we don't know how many terms it is going to be greater than 1,000,000, and we know what our formula is. It's A times 1 minus R to the n over 1 minus R. And we want that effectively to be greater than 1,000,000. So we substitute everything in. 5 times 1 minus 2 to the power n over 1 minus 2 has to be greater than 1,000,000. So, well, let's sort this out. I sort out, well, what's the denominator? Well, that's going to be minus 1. So what's this? So that's going to be minus 5. So I would divide through by minus 5, and I'd have 1 minus 2 to the power n is greater than minus 200,000. Okay. Hopefully that was okay. If you want to do it one step at a time, you can. If you wanted to multiply by minus 1 and then divide by 5, that would be okay. But you've just got to get rid of the denominator and then get rid of the number in front of the bracket. I would add the 2 to the power of n. So I'd have 1 is greater than 2 to the power n of minus 200,000. And then I'd add the 200,000. So I'd have 200,000 and 1 is greater than 2 to the power of n. Okay. You could do that in one step. And then I would take my logarithm to the base 2. So I'd say log to the base 2 of 200,001 is greater than, n. And log to the base 2, 2 is greater than 1, so we know this is positive, so I don't have to worry about changing that inequality the other way around. And if I put that in my calculator, so log to the base 2 of 200,001, and you would get 17.609 is, so n has to be less than 17.6, so n must be 17. Okay, now I've got to be honest, I would always check, because sometimes those inequalities don't quite work. Okay, because to me that doesn't seem the right way round. I'll be honest. I think I might have made a mistake somewhere, but I can't see where. So we'll try it. Let's try it out, because I am a bit dubious. So let's do s to the 17. So it's going to be 5 times 1 minus 2 to the 17 over 1 minus 2. And I'm going to put it in my calculator. 5 brackets 1 minus 2 to the power 17 over 1 minus 2. Yeah, you see, I thought that was wrong. It's 655,355. So s to the 18, if I do it again with the power of 18, delete 18, yep, is 1,310,715. Right, so what did I do wrong here? So it has to be greater than 1,000,000. So that's definitely right. So that I can't see it, but I'll come back to you and see if I can work it out another time and explain it a different time, because I need to move on really. Okay, I don't want to make this video too long. Right, and then we might have a question like this. So it's getting you to show something and then hence find the value of k. So a geometric series has the first term of 20, a common ratio of 4/5, which I'm going to write as 0.8 because the answer's in decimals anyway. And we want to know when Sn is greater than 50. So again, we want to know when a 1 minus r to the n over 1 minus r is greater than 50. Oh, I've just remembered what I did. When you divide by a negative number at this point here, what happens when you divide by a negative number? You have to change the sign of the inequality. Honestly, just remember, just as I was doing that other one. Right, going back. So I've got 20, 1 minus 0.8 to the power of n over 1 minus 0.8 is greater than 50. So again, personally, I sort of like put this together. So I go 20 divided by 0.2, because that's what you've got here. In your denominator, you've got 0.2. So 20 divided by 0.2 is 100. So that becomes 100. So then you divide by 100 both sides, and you'd have 1 minus 0.8 to the power n is greater than a half, because 50 divided by 100 is a half. And actually I'm going to change it into decimals. Okay, so then add 0.8 to the power of n to both sides, take away 0.5. So I'm going to take away 0.5 from both sides. I'm going to add 0.8 to the power n to both sides to get that on the other side. And I'd have 0.5 is greater than 0.8 to the power of n. This is one where you've got to take logarithms of both sides. So the natural logarithm of 0.5 is greater than n times the natural logarithm of 0.8. I hope we can do that this quick now, taking that power out from inside the argument. And so we have n is less than the natural logarithm of 0.5 over the natural logarithm of 0.8. And hopefully, I used the letter n instead of k, but they'll condone that. So k is greater than. Now, this is the other thing you've got to remember. A natural logarithm of less than 1 is a negative number. So at that point, when you do the division, you have to change the way of this. You have to change the sign of the inequality. It has to flip around, and I forget it every single time. I do apologise. So, and then it says find the value of k or n. We've used n, it doesn't matter. So we just say natural logarithm 0.5 divided by the natural logarithm of 0.8 equals, so n has got to be greater than 3.1, so n must be 4. Okay, right, here's some for you to have a go at. So just be careful with those natural logarithms. Just be careful when you've got inequalities. Think about, are you dividing by a negative number? Because that changes the way the inequality goes. Press pause. When we've finished, press play and we'll have a look. Okay, so here we go. First two. Fairly straightforward, like my first couple of examples. You just need to work out how many terms there are first, and then you can work out the sum of those number of terms. So in the first case it was 8 terms, and you should have got 1275. For the second one, again, the first and the hardest step really is working out how many terms there are. So you know the last term is 2. So again, you're going to end up with n equals 9. Okay, and so when you do the sum of the 9 terms, you get 19,682. The final one of these, again, you've got your finding out what your number of terms are. Remember, it's this negative thing. It's not that you can't take that. So remember, we sort of like multiply through by a negative so that we can work out that n is 9. And hopefully then you got the sum of the 9 terms was 2019.5. Okay. So, number 2. This was one where you had to do what we did last lesson to work out what your first term and your common ratio are first, because it doesn't tell you the first term, it told you the 4th term and the 5th term. And once you've done that, it actually tells you how many terms it wants you to work out the sum of. So you find the sum of the 20 terms is 3,145,725. Okay, 2 more to go. Very similar to my last example, this one. Okay, so again, you should have got that n is 4. Remember, this, oops, didn't mean to do that. This logarithm here is going to be a negative number, so it swaps direction at that point, and you've got n has to be greater than 3.15, so again, n equals 4. And the last one, so we want our sum to exceed 2,000. We know our common ratio is 2/3, okay? And so we go through again. Remember, the natural logarithm of 2/3 is going to be a negative number, so it swaps direction at that point. If you're not sure, just put it in your calculator and check first. Always check what you're dividing by. Is it positive or is it negative? And you should have got n equals 7. And that's it for today. So next lesson, we'll do a thing called summing to infinity. So have a go at the questions that I've put on Edmodo, and I'll speak to you next lesson.